Hello everyone. Here is the notes for D and F block elements and it is useful for the students of class 12th for board examinations. I wish everybody to prepare well for the board examination and get good marks. Please subscribe my channel GVS Chem at 4093. D and F block elements. This is the revision notes for the students of class 12 for board examinations. D block elements are placed in between S and P block elements in the periodic table. Their general electronic configuration is N-1 D 1 to 10 NS2. S block elements are kept at extreme left of the periodic table, whereas P block elements are kept on the right extreme right of the periodic table. S block elements are active metals, whereas P block elements are less active metals, including non-metals. The regular gradation or change in the properties of elements from more active S block elements to less active P block elements take place through D block elements. Thus, D block elements are also called as transition elements. Transition elements may be defined as the elements whose atoms are simple ions contain partially filled d orbitals. This is the scheme of the periodic table or outline of the periodic table. S block elements are here, P block elements are here. In between, S and P block elements contain 1 and 2 groups, whereas P block elements contain 13 to 18 groups, whereas D block elements they are elements of groups from 3 to 12, and these D block elements are in between S and P. S block elements or P block elements are together known as representative elements, whereas D block elements are transition elements, because transition means change. The change in properties from left to right takes place through the D block elements, therefore they are transition elements. Down below the table, there are inner transition elements or F block elements. In F block elements, the outermost last electron enters into anti-penultimate F subshell. Therefore, they are referred as P block elements. They are also referred as inner transition elements. They are lanthanoids. Lanthanoids are the elements from atomic numbers from 58 to 71, whereas actinoids are the elements from atomic numbers from 90 to 103. Now, the definition of transition elements does not cover zinc, cadmium, mercury, as these elements have completely filled d orbitals in their atoms or ions. For example, zinc electronic configuration is 3d10 4s2, whereas zinc 2 plus ion configuration is 3d10. So 3d10 means it has all the 5 d orbitals are filled with electrons, whereas cadmium atomic number 48 configuration 4d10 5s2, whereas cadmium dipositive ion configuration is 4d10 5s0. In the same manner, mercury atomic number 80 and its configuration is 4f4 5d10 6s2, whereas dipositive ion of mercury has 4f4 5d10, that is d orbitals are completely filled with electrons, hence they do not come under transition elements. In the above atoms or their ions, they have fully filled d orbitals, hence they are not referred as transition elements, simply they are d block elements. In transition elements, d orbitals of penultimate shells are progressively filled. There are mainly 3 series of transition series, that is first series of transition metals are scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. These are third transition first series of transition metals, or they are also referred as a 3D series since the last electron enters into 3D subshell. These first series of transition elements, they belong to 4th period. In these series, the last electron enters into 3D subshell, hence they are referred as a 3D series or first transition series. In the same manner, second series of transition metals are yttrium, zirconium, nobelium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium. These elements, the second series of transition elements, they are also referred as 4D series, as the last electron enters into 4D subshell and they belong to fifth period. Whereas third series of transition metals are lanthanum, hafnium, tantalum, wolfram, rhenium, osmium, iridium, platinum, silver, mercury. This is gold. Au means gold. And third series of transition metals belong to sixth period and the last electron enters into 5D subshell. Hence, therefore, they are referred as a third series of transition metals or 5D series. Electronic configurations. See, elements zinc, cadmium, mercury, they have completely filled d orbitals in their atoms or their simple ions. These metals are not regarded as transition metals. The general configuration of d block elements are n-1d, 1-1 to 10 or ns 1 to 10. Some of the elements in 3D, 4D, 5D series, they have exceptional configuration due to the half filled orbitals and due to which they get the stability. For example, copper configuration is copper electronic configuration is expected configuration is 3d9 4s2, but if copper gets one more electron into the 3d subshell, it gets the maximum stability. Therefore, it has the exceptional configuration 3d10 4s1. In the same manner, nobelium has a configuration 4d4 5s1. It has 4 unpaired electrons in the 4d subshell instead of having a normal expected 4d3 5s2 configuration. In the same manner, molybdenum has a 4d5 5s1. If we write all the elements one under the other, that is 3d series, 4d series, 5d series, the elements shown within the red line, they have exceptional configuration, that is copper, nobelium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, platinum, gold. They have exceptional configuration, and of course this shape is a key of a lock. So electronic exceptional configuration can be remembered very easily. That is, the elements present within the boundary line of a key of a lock, they have exceptional configuration, and of course they have NS1 configuration, whereas all the remaining elements which are outside the boundary line of this key of a lock, they have the configuration NS2. And accordingly, depending on the atomic number, number of electrons follow in the D subshell. These are the exceptional configuration. Already we discussed. Gold has exceptional configuration AU, Xe54, 4f14, 5d10, 6s1. While filling the electrons, the last electron enters into penultimate D subshell, whereas if the atom loses an electron to form cation, it loses electron from the valence subshell. That means when the last electron fills during the electronic configuration, it enters into D subshell, whereas when it is losing electron, the electron loses from the NS subshell. General properties of transition elements. All the transition elements are metallic in nature. Zinc, cadmium, mercury, manganese are exceptions, as they do not have typical metallic structures. Transition elements exhibit typical metallic properties such as luster, that is shining surface, high tensile strength, ductility, malleability, and high thermal and electrical conductivity. They show gradual decrease, that is regular decrease in the electropositive character in moving from left to right. The metallic bonds in transition metals are quite strong. Due to the presence of strong metallic bonds, the transition metals are hard, possess high densities and high enthalpies of atomization. Because the large number of unpaired electrons in d orbitals of their atoms, they have a stronger interatomic interactions and hence a stronger metallic bonding between atoms, resulting in higher enthalpies of atomization. Second and third transition series have greater enthalpies of atomization than corresponding elements of the first series. This factor is used in accounting for the occurrence of many heavy transition metals. Most of the transition metals have higher densities. Iridium having highest density of 22.6 gram per decimeter cube. 6 gram per decimeter cube. Atomic and ionic radii. Atomic and ionic radii of transition elements are smaller than S block elements but larger than P block elements. Among the elements of the particular transition series, as the atomic number increases, atomic and ionic radii decreases till the middle, becomes almost constant and then increases towards the end of the period. Atomic radii of the first transition series decreases from scandium to chromium, remains almost constant till copper and increases towards the end. The decrease in size in the beginning is due to the increase in nuclear charge. However, the increase in nuclear charge partially cancelled by the increased screening effect. Increased screening effect of electrons in the d orbitals of the penultimate shell. When the increase in nuclear charge and the increased screening effect balance each other, the atomic radii almost constant. Increase in atomic radii towards the end is due to the electron-electron repulsions. The repulsive interactions between d orbitals become very dominant towards the end of the period and cause the expansion of electron cloud and thus resulting in the increase in size. Atomic radii of second and third transition series are greater as compared to the first transition series. The elements of second and third transition series belonging to particular group have almost equal atomic radii. This is due to intervention of the 4f orbitals which must be filled before 5d series of the elements. The filling of 4f before 5d orbitals results in a regular decrease in atomic radii, and this is called lanthanoid contraction, and this compensates for the expected increase in atomic size on moving down the group with increase in atomic number. For example, fourth group elements titanium, zirconium, hafnium. Titanium atomic size is 132 picometer, whereas titanium belongs to fourth period and zirconium belongs to fifth period. The atomic size of zirconium is 160 picometer. There is a increase from titanium to zirconium, whereas hafnium belongs to sixth period. From fifth period to sixth period, the size is almost same. This is due to the lanthanoid contraction. And here you can observe this is a third series, the 3D series, 4D series, 5D series. So 3D series, 5D series here. So there is a regular increase from 3D series to 4D series, but from 4D series to 5D series the increase is very less. Ionization enthalpies and electrode potentials. Ionization enthalpies of transition elements increase from left to right. The relative difference of ionization enthalpy values of any two consecutive D block elements of the particular period is much smaller than those of S and P block elements. The increase in ionization enthalpies is primarily due to increase in nuclear charge. As a gradual filling of d orbitals with electrons in transition elements, the effect of increase in nuclear charge is partially cancelled by increase in screening effect. Consequently, increase in ionization enthalpy along the period of D block elements is very small. 5D transitions metals have higher values of ionization enthalpies than 4D, 3D and 4D series, and it is due to the greater increase in nuclear charge as there is intervening 4f electrons. Significance of ionization enthalpy values. Ionization enthalpy values give some idea of energy required to raise the metal to a particular oxidation state. From the values of ionization enthalpies of the metals, it is possible to know the relative stability of various oxidation states. For example, if we consider nickel and platinum, the sum of the first two ionization enthalpy values and sum of the first four ionization ionization values are given here. Nickel has 2.49 into 10 to the power 3 kilojoule per mole, whereas platinum has 2.66 into 10 to the power 3 kilojoule per mole. As the sum of the first ionization enthalpies is less for nickel, therefore Ni2 plus oxidation state is stable when compared to Pt2 plus. In the same manner, nickel 4 plus, that is the first 4 ionization, sum of the first 4 ionization enthalpy values for nickel is 11.29 into 10 to the power 3, whereas for platinum, sum of the first 4 ionization enthalpy values are 8.36 into 10 to the power 3. Therefore, as for platinum, the sum of the first 4 ionization enthalpies of platinum is less when compared to nickel. Pt4 plus ions are stable when compared to Ni4 plus. Other factors that determine the stability of a particular oxidation state in solution are the enthalpy of atomization and hydration enthalpy. So here in this schematic diagram, metal, this is solid, whereas metal gas, this is from here to here atomization takes place. From here to here ionization enthalpy, that is metal in gaseous state loses electron and it becomes M plus, and from M plus it dissolves in the solution, whereas here this is enthalpy of atomization, enthalpy of ionization, this is the enthalpy of hydration. The total enthalpy change is equal to delta HA plus delta HI plus delta H hydration. Smaller the value of total enthalpy change for a particular oxidation state of the metal, greater will be the stability of oxidation state. That means if the sum of these 3 enthalpies is least, then stability of a particular oxidation state is more. The electrode potentials are the measure of the values of total enthalpy change. So total enthalpy change is the measure of electrode potentials. Lower the standard electrode potential, more is the stability of oxidation state in aqueous solution. That means if the oxidation potential is less, stability of a particular oxidation state in solution is more. And enthalpies of atomization, enthalpies of ionization and enthalpies of electrode potentials of first transition series are given here. Trends in M2 plus M standard electrode potentials. The E0 values for M2 plus oblique M from the adjacent figure indicates the decrease in tendency to form divalent cations. See here, for titanium, electrode potential is least, whereas vanadium it is more, chromium it is more, manganese is least. These less negative values of E0 is related to the sum of the first and second ionization enthalpies. From the graph it is observed that copper has a positive electrode potential. This is due to the greater amount of energy required to transform copper into Cu2 plus ion, and it is not balanced by the enthalpy of hydration. Due to the positive electrode potential, copper does not liberate hydrogen from dilute acids. Only oxidizing acids such as nitric acid, hot concentrated sulfuric acid react with copper. E0 values of manganese, nickel, zinc are more negative than expected from the trend. M2 plus oblique M equal to E0 value for Mn is minus 1.18. This is because after losing 2 electrons, manganese gets all 5 unpaired electrons in d orbitals, therefore it gets the stability. So higher the stability, least is the electrode potential, or vice versa. In the same manner, nickel 2 plus ion electrode potential is minus 0.23. Now then the negative electrode potential of nickel is due to the negative enthalpy of hydration. Electrode potential of zinc is minus 0.76. Zinc has fully filled d orbitals as shown here. Therefore, since fully filled d orbitals of zinc, it gets the negative electrode potential. As ionization enthalpies and enthalpy of atomization of d block elements do not show any trend, the electrode potentials also do not show any regular variation. The trends in M3 plus oblique M2 plus standard electrode potential. E naught values of M3 plus oblique M2 plus values for the some metals of 3D series are given in the table. From these values it is clear that there is no regular trend or variation in M3 plus oblique M2 plus electrode potentials. See here, this is the table. This is M3 plus oblique M2 plus. For titanium it is minus 3.7, for vanadium minus 2.6, for chromium minus 0.41, for manganese it is plus 1.57. That means as the value for M3 plus oblique M2 plus for manganese is positive, that is M3 plus ion is not ready to form. In the same manner, iron, cobalt also. Because in M2 plus ion it is more stable as the d orbitals are half filled. As Sc3 plus is more stable as it gets the noble gas configuration, that is a 3d0 here. 4s0, 3d0, noble gas configuration, that is argon configuration. M3 plus oblique M2 plus Mn2 plus E naught value is plus 1.57. The high E naught value is due to the reason that M2 plus has a d phi configuration, and due to this M2 plus ion has stability. Mn2 plus configuration is 3d5 4s0, 5 unpaired electrons. In Mn3 plus it has 4 unpaired electrons. That means one d orbital is deficient of electron. Therefore, it is not ready to form Mn3 plus from Mn2 plus. Or otherwise, Mn3 plus ion is ready to take the electron. That is, Mn3 plus undergoes reduction by taking the electron, or it acts as oxidizing agent for other substances. In the same manner, Fe2 plus oblique Fe2 plus Fe3 plus oblique Fe2 plus couple, the value of E naught is comparatively low. That is, E naught value is plus 0.77 because Fe3 plus has a d phi configuration. That means Fe3 plus has a d phi configuration, whereas Fe2 plus has one paired electron. Therefore, Fe2 plus is ready to lose the electron. That means it acts as reducing agent, or Fe2 plus undergoes oxidation easily. This is Mn3 plus Mn2 plus. 4 unpaired electrons, 5 unpaired electrons. This is CO3 plus 6 electrons. That is, in one orbital there is one lone pair, whereas in CO2 plus 2 orbitals have low pairs. The above E naught values indicate that Mn3 plus and CO3 plus are strong oxidizing agents. That is, Mn3 plus CO3 plus, they are ready to take the electrons. That is, they are oxidizing agents. They take an electron from the other substances to get a half-filled configuration. Other substances undergo oxidation. Mn3 plus and CO3 plus, they are a strong reducing agent. This is reducing agents. They take an electron from the other substances, whereas other substances undergo oxidation. E naught values of M2 plus oblique Mn couple are for most of the first transition element metals are negative. These metals are more reactive and are oxidized by 1M H plus solution, that is dilute acids. These metals can displace hydrogen from dilute acids. The exception is copper. Copper with positive electrode potential plus 0.34, it does not displace hydrogen from the dilute acids. This is due to the reason that enthalpy of atomization and enthalpy of sublimation is not balanced by enthalpy of hydration. The electrode potential of the metal couple is positive. Atomization is smaller than enthalpy of hydration. The electrode potential of the metal couple is negative. Therefore, copper, as it has a positive electrode potential, it does not displace H plus ion from the dilute acids. The negative E naught values for the redox couple are Ti3 plus oblique Ti2 plus V3 plus oblique V2 plus Cr3 plus oblique Cr indicate that Dipositive ions of titanium, vanadium, chromium are strong reducing agents. That is, they are ready to give the electron. Oxidation states. Transition metals show variable oxidation states due to the participation of Ns electrons and N-1d electrons in bonding. The lower oxidation state is generally exhibited by Ns electrons when Ns electrons take part in the bonding, and higher oxidation states is exhibited when N-1d electrons participate in the bonding. It is noted that oxidation states of transition elements differ from each other by unity, whereas oxidation state of non-transition elements, that is S block and P block elements, differ by 2. That is, oxidation state of manganese Mn2 plus 3 plus 4 plus 5 plus, the oxidation states differ by unity, whereas oxidation states of say platinum 2 plus platinum 4 plus, they differ by 2 units. Some of the features of oxidation states of transition metals. In each group, the highest oxidation state increases with increase in atomic number, reaches a maximum in the middle, and then decreases. For the first transition series, the maximum oxidation state is exhibited by manganese, that is plus 7 oxidation state. The elements which exhibit the maximum number of oxidation states occur either in the middle or near the middle of the series. In first transition series, manganese exhibits maximum number of oxidation states, that is plus 2 to plus 7. Elements in the beginning of the series exhibit fewer oxidation states as they have a smaller number of electrons which they can lose or contribute for sharing. Elements at the end of the series exhibit fewer oxidation states because they have more number of d electrons and hence fewer vacant d orbitals which can involve in bonding. For elements of first transition elements except scandium, plus 2 oxidation state is the most common oxidation state. This oxidation state arises due to the loss of 4s electrons. The transition elements in lower oxidation states, that is plus 2 and plus 3, generally form ionic bonds, whereas in higher oxidation states the bonds formed are essentially covalent. In chromate ion, that is CrO4 2 minus, the bonds formed between chromium and oxygen are covalent bonds. In P block elements, the lower oxidation states are favored by heavier members due to inert pair effect, whereas in case of D block elements, the higher oxidation states are more stable for heavier members. That is, for P block elements, lower oxidation states are stable. For D block elements, higher oxidation states are stable. Cr4 plus in the form of dichromate ion in potassium dichromate acts as a strong oxidizing agent in acidic medium, while MnO3 and WO3, manganese trioxide and wolfram trioxide, are not act as reducing agents. Thus, Cr4 plus and Cr3 plus are more stable. Cr2O7 plus 14H plus 6 electron gives Cr3 plus and 7H2O, whereas E naught value is 1.33. That means in acidic medium, H plus indicates acidic medium. In acidic medium, dichromate ion, it takes electron from the other substances, therefore it undergoes reduction, whereas this ion acts as a oxidizing agent. Since Cr2O7 plus ion takes electrons to get reduced and act as oxidizing agent. The highest oxidation state shown by any transition metal is plus 8. For example, in ruthenium and osmium, they show highest oxidation state, that states of plus 8 in some of their compounds. Low oxidation states are formed when a complex compound has ligands capable of pi acceptor character. Some transition metals also show oxidation state of 0 in their compounds. That is, tetracarbonyl nickel. Nickel has a 0 oxidation state. Disproportionation reactions. A reaction in which a single substance undergoes change to produce products, one of which is in higher oxidation state and the other is in lower oxidation state, and such reactions are called disproportionation reactions. For example, Mn3 plus in aqueous changes to MnO2 with a higher oxidation state, Mn2 plus with lower oxidation state. In the same manner, permanganate ion in the acidic medium changes to permanganate ion with a higher oxidation status, that is plus 7. Plus 6 changes to plus 7, that is oxidation takes place. And plus 6 changes to plus 4, that is oxidation state decreases and reduction takes place. So, oxidation and reduction takes place in the same reaction. This is known as a disproportionation reaction. In the same manner, in organic chemistry also, formaldehyde undergoes oxidation as well as reduction. This is a Cannizzaro reaction. So this is also disproportionation reaction. Trends in the stability of higher oxidation states. Transition metals show highest oxidation states in their complexes of oxygen and fluorine. Fluorine can stabilize the highest oxidation state, as fluorides of transition metals can have higher lattice energy or higher bond enthalpy. Oxygen can stabilize higher oxidation state of transition metal in its compounds by forming multiple bonds. That is in this is dichromate ion. In dichromate ion, what happens? Multiple bonds are formed. Whereas chromium hexafluoride, what happens? It has higher bond enthalpy. The highest oxidation states are achieved in tetrahalides of nickel. Oxidation state of nickel is plus 4. Oxidation state of vanadium in VF5 is 5. CrF6 is 6. Manganese cannot show highest oxidation state in simple halides, whereas it shows a maximum oxidation state of plus 7 in MnO3F, that is manganese trioxyfluoride. Vanadium shows plus 5 oxidation state only in VF5. Other pentahalides of vanadium are unstable and undergo hydrolysis to give oxohalides. Fluorides are unstable in the lower oxidation states of metals. Vanadium exhibits oxidation states of plus 2 and copper oxidation state is plus 1 only in their chlorides, bromides and iodides. All the copper 2 plus ions, copper 2 plus halides are known except copper iodide, whereas Cu2 plus oxidizes I minus to I2. Many Cu plus compounds are unstable in aqueous solutions and undergo disproportionation. So here is the table for halides of 3D series of metals, and here are the oxides of 3D series of metals. Transition metals also exhibit highest oxidation state in their oxides. The ability of oxygen to stabilize higher oxidation state is much more than that of fluorine. Highest oxidation state is exhibited by manganese is plus 4 with fluorine, whereas the highest oxidation state exhibited by manganese in its oxide is plus 7. Oxygen is able to form multiple bonds with the metal. Thus, it can stabilize the maximum or highest oxidation state. The highest oxidation state in oxides coincides with the group number, and it is attained in the elements from scandium to manganese. Beyond group 7, no higher oxides above Fe2O3 are known. Thank you. Students are advised to revise this lesson and prepare well for examination.